webinar. Okay, good morning, good afternoon, good evening, everyone. So welcome to the Azure Data webinar. Today, a great pleasure to have Dr. Avishek Rudra speaking with us. So Avishek got his undergraduate degree back then in presidency. Then he went to IIT for his master's before he started his PhD at University of Minnesota. Actually, most of today's works talk that is going to talk about what the work that he did, part of the work that I did at University of Minnesota for his PhD degree. So currently, Avishek is working on his postdoctoral research project at Cambridge University, although physically he's in Scotland now, on the road. So with that, I was give a rest on for Avishek to tell us about the ferric iron partitioning between pyroxene and melt, and talking about its implications for the MORB and OIB source mantle. So with that, Avishek, please go ahead and please leave about 10-15 minutes for interaction with our participants, or even longer for our interaction with our participants, because Zoom webinar normally is more flexible. So go ahead.
Okay, thank you, Johnny. Thank you everyone for tuning in today. I will share a part of my work that I did as a part of my PhD at the University of Minnesota, which involves understanding ferric iron partitioning between pyroxene and melt, and what it means for ferric iron content of the upper mantle and the oxygen fugacity of the upper mantle. So just to give you a brief introduction of what oxygen fugacity is, oxygen fugacity is the partial pressure of oxygen in a system. And in case of the Earth's interior, you don't have free oxygen. So the way we measure oxygen fugacity is by writing out reactions which involves oxygen. For example, in the shallow upper mantle, we can write out a reaction between different phases, like olivine, phthalate component in olivine reacts with oxygen to produce a ferrocylate component in OPX and the magnetite component in spinel. So we can write out this reaction and measure the chemical potential of oxygen in that system, which can then be transferred as or translated as the oxygen fugacity of the system. Notice that the oxygen fugacity is written as a function of temperature and pressure. So the absolute oxygen fugacity of the system is a function of temperature and pressure. To reduce that effect, or to reduce that effect of temperature and pressure on the absolute oxygen fugacity, we oftentimes, what we do is we represent or report oxygen fugacity as a delta value, like delta QFM, which is the difference between the oxygen fugacity of the system of our interest from the oxygen fugacity of a hypothetical buffer, such as QFM, quartz, phthalate, magnetite. Such a buffer doesn't exist in the mantle, but just for our convenience, we report oxygen fugacity of a system as the difference between the FO2 of the system from the FO2 of the QFM buffer, which minimize the reason we do that, it minimizes the effect of temperature, pressure, and oxygen fugacity. So therefore, the delta QFM becomes more or less, or rather less sensitive to temperature and pressure, but more sensitive to the amount of oxygen in the system, and the phases that are present in the system, and so on, which are our interest. And so if you look at this figure on the left, you can see that the oxygen fugacity is one of the thermodynamic intensive variables that varies quite a lot, starting from the surface of the Earth to the very lower part of the Earth's mantle. So as we know, the atmosphere is quite oxidized. It has 21% oxygen. It has free oxygen. But as we go into the Earth, the oxygen is bound to the minerals of the upper mantle, and the very shallow part of the upper mantle, you have a considerable amount of both ferric iron and ferrous iron. But as you go deep into the upper mantle, the amount of ferric iron goes down, and ultimately the mantle becomes saturated in Fe0, which is metallic iron. So the oxygen fugacity progressively reduces as we go down, although it's not a constant reduction. There are patches of the mantle where you get anomalously high or low oxygen fugacities. So overall, there is a decrease in oxygen fugacity starting from the very shallow part of the upper mantle to the lower part of the lower mantle. So that's a bit introduction about why we care about oxygen fugacity and what it is. And why do we why do we need to understand oxygen fugacity for the upper mantle? And that's because there are multiple reactions that happen in the Earth's upper mantle, which depends on the amount of oxygen that is there in the system. For example, when we talk about the redox melting, which is the oxidation of native carbon, which is C0, to carbon dioxide, which can induce melting in the Earth's mantle, that redox reaction depends on the amount of oxygen, the amount of ferric iron which is in the system. Other reactions, such as the stability of or the appearance of metallic alloy, also depends on the amount of ferric iron or the amount of oxygen in the system. So in order to understand the depths at which these reactions can take place, we need to understand what the ferric iron system is. So for example, right, if we have, so this is the ferric over Fe total, which is the ferric iron content versus the total iron of the upper mantle peridotite. And you can see that as the amount of ferric iron in the system goes up, the depth at which these reactions occur also goes down. So to understand the depths better, we need to understand the values of the x-axis better. So that's kind of the motivation, first motivation. What is the ferric iron content of the upper mantle? And there are several studies previously which have looked into this problem from different perspectives. For example, there are multiple studies who have measured the ferric iron content of the minerals in the xenoliths from the continental lithospheric mantle, and they have provided us like a range of values from 0.02 to 0.038. That's kind of the values that they have found the xenoliths have in the continental lithospheric mantle. But remember, for our discussions, we are more interested in what's happening in the convective or the asthenospheric mantle, which may or may not have the same amount of ferric iron as the continental lithospheric mantle. So we don't have a direct evidence, or we don't have a direct data on what the ferric iron content of this mantle looks like. We have a data of this part of the mantle. So it's still, this part is still unknown. However, it gives some constraints, right? So, and the other way that people have looked or tried to measure the ferric iron content of the mantle is by measuring ferric iron content of the basalts. As you know that about 10 years ago, Lise Cottrell and company invented, or actually developed, the method by which you can very precisely and accurately measure ferric iron in basaltic systems and basaltic classes. So by measuring the ferric iron content of the basalts and assuming a certain partition coefficient of ferric iron during partial melting of the mantle, you can back calculate what the source ferric iron content was like. And by doing so, directly from measuring basaltic ferric iron as well as measuring ferric iron in the experimental system, in the experimental glasses, Cochran and Kelly 2011 and Davis and Cottrell 2021, they have provided two different values of the ferric iron of the upper mantle, and that's between 0.034 to about 0.055. So notice that none of the values are actually converging to one another. They're sort of getting more and more diverging as time progresses. So there's still quite a debate about what the ferric iron content of the upper mantle is, and it varies from about 0.02 to 0.055 at the moment. And lastly, there is a purely thermodynamical way of knowing what the or estimating what the ferric iron content of the upper mantle looks like. And in 2016, and the tool is PMEL, so there are other thermodynamic models that are available as well. But in 2016, Glenn Gattani estimated what the ferric iron content of the upper mantle might look like in order to satisfy the FO2 of the upper mantle that we know. And he came up with a value of 0.06. So you can see there's a factor of 3 difference in our estimation of the ferric iron content of the upper mantle. It starts from 0.02 to 0.06, and therefore, since we don't know what the value looks like, the depth of redox melting can vary from somewhere between 75 kilometers to somewhere close to 200 kilometers. So I set out to understand what the ferric iron content of the upper mantle looks like, and from which we can then estimate the depth of these redox reactions. And secondly, there's another sort of an indirect motivation to this study, which is when we look at the mid-ocean ridge basalts globally and look at the ferric iron content and the sodium content, which is corrected for olivine fractionation, that's why it's 8, that is corrected to NGO 8%. When we look at that, this correlation in global mid-ocean ridge basalts, we see that there is a negative trend, right? Which is quite opposite what we expect if we consider ferric iron is incompatible. We know that sodium is incompatible during partial melting of pyrrhotite, but if we consider ferric iron is also incompatible, then we expect a positive correlation. However, we do see a negative correlation. So that means either ferric iron is not compatible during partial melting of pyrrhotite, or the compatibility is different depending on where you are, depending on whether it's low degree melting or high degree melting, the ferric iron compatibility might change. So we need to understand that as well. And thirdly, and for the last motivation why we delved into this study, and that is when you look at the ferric iron content of the medusa-rich basalts versus the ferric iron content of the ocean island basalts, we see that the OIBs are systematically offset to higher ferric iron compared to the medusa-rich basalts. And previous studies have attributed this to the fact that there is recycled lithologies in the source region of ocean island basalts, and those recycled lithologies could be more oxidizing, which imparts this oxidized character to the ocean island basalts. But the problem with that model is that they don't take into account the fact that ocean island basalts are generated at different conditions compared to the medusa-rich basalts. They're generated where garnet is present. They're usually represented at, they're usually generated at a deeper part of the mantle, and usually represents a smaller degree of partial melting compared to the medusa-rich basalts source regions. So before we can talk about the source effect, before we can talk about the source heterogeneity, we need to understand what melting, purely the effect of melting does to the ferric iron content of these basalts before we can talk about the heterogeneity in the source. So this difference, 0.018 to 0.14, that difference could, or some of the difference could be coming from the fact that OIBs are generated at different conditions compared to the medusa-rich basalts. So we'll also try to understand that in this talk. So with that, yeah, that's exactly what I told, that OIBs are generated different conditions compared to the MORBs. So we need to understand the effect of melting to generate this difference in ferric iron before we can talk about the source heterogeneity. So when we talk about the ferric iron content of the upper mantle, what are the phases of interest? We see that in the upper mantle, CPX and OPX, both in spinel pyrrhotite as well as garnet pyrrhotite, CPX and OPX hold the highest amount of ferric iron. These minerals in pyrrhotite roughly holds about close to 70 to 80% of ferric iron in the upper mantle. Spinel is very rich in ferric iron, but because spinel abundance is like 2% in the pyrrhotite, in a fertile pyrrhotite, it has a very low leverage or rather it has a very low reservoir capacity to the ferric iron content of the upper mantle. So in order to understand how ferric iron partitions during partial melting of pyrrhotite, we need to understand how ferric iron behaves during partial melting of CPX and OPX. Right, so these are our main phases of interest for our purposes. And not only that, not only these are the main reservoir of ferric iron in the upper mantle, they also indirectly affect the oxygen fugacity of the upper mantle. For example, if you look at this plot on the right, it shows in the right, it shows, it's one of the plots from the Stolper et al. 2020 study. It shows that the abundance of OPX and CPX sort of mimics the way the FO2 of the system change, right? So both the absolute FO2, which is a log of FO2, as well as the FMQ, delta FMQ, which is the relative oxygen fugacity change, sort of mimics the way the CPX and OPX abundances are also changing. So they are not only reservoir phases of ferric iron in the upper mantle, but they're also indirectly influencing what the oxygen fugacity of the subsolidus pyrrhotite or the upper mantle pyrrhotite would look like. So these are very important phases to understand from the prevalence of ferric iron. So there are multiple, so this is like the overall motivation and the reason of studying ferric iron pyroxenes in the context of partial melting of pyrrhotite. But there are multiple problems or the multiple barriers to it, to understanding this problem. One of the problems is that how we measure ferric iron in the pyroxenes. There are already developed methods, bulk methods that are available. For example, with chemistry or conventional Mosfire spectroscopy, but you can see that the analysis area is about 1 millimeter to 2 to 3 millimeters. So these are bulk samples where you need to where you need to separate out the pyroxene crystals, crush them up, and make a bulk mount where you can measure them with conventional MOSBAR spectroscopy. Even the very recent MOSBAR milliprobe has an analytical volume of about 50 micron to 100 micron. So those are also not, these are great methods for measuring ferric iron and pyroxenes for natural samples where you have large pyroxene crystals. You can easily separate them out and crush them up to measure their bulk in a bulk, but they're not very well suited for measuring ferric iron in experiments where you have pyroxenes or crystals hardly in the size of 50 to 100 microns. So these tiny crystals, very difficult to separate out, and often they are embedded within the glass. So you need a microbeam method like a microprobe or some other method in order to measure ferric iron. So you need something like this method, which you can use then to measure the ferric iron in the experimental pyroxenes. So what we did, we set out to collect a bunch of pyroxene crystals all over the world from different museums so that we can use those as our standards to develop a microbeam method. So we collected these pyroxene crystals, which are homogeneous in their composition, which are inclusions-free, and then we crushed them up and measured their ferric iron content using MOSBAR spectroscopy. So the way, I'll not go into details of this, but the way you can measure ferric iron is that with MOSBAR spectroscopy is that the amount of ferric iron versus ferric iron is ferrous iron is proportional to the absorption area of the ferric iron with the ratio of absorption area of the ferrous iron. So the absorption areas of these doublets, the areas of these doublets are directly related to the amount of ferric iron versus ferrous iron we have in the sample. So you use those to measure, we use the MOSBAR spectroscopy to measure the ferric iron content of our pyroxene standards, both CPX and OPX standards. And then we need a microbeam method. For us, the method of choice is X-ray absorption spectroscopy, X-ray absorption near structure spectroscopy. Zane spectroscopy has been widely used now in earth sciences to measure not only ferric iron, but to measure valence of many elements, including vanadium, titanium, iron, sometimes copper, in different systems, like in glasses, in different crystals. And this has been previously developed, very well developed for example, for silicate glasses. This is a very well developed technique to measure ferric iron in silicate glasses, where you use this part of the spectra, which is called the pre-edge, and then try to fit Gaussian curves to these regions, and then extract the centroid energy, which then correlates with the amount of ferric iron you have in the system. So as the system becomes more and more oxidizing, the centroid energy becomes higher and higher, which then correlates with the amount of ferric iron in the system you have. So we used a similar technique. We used the Zen's technique, but for pyroxenes. This is very well developed for glasses, but we developed it for pyroxenes, both for CPX and OPX. But there is a problem, and that is pyroxenes are anisotropic in X-ray absorption. Just like you see pyroxene, when you put a pyroxene crystal, thin section pyroxene crystal under optical microscope, you see it has birefringence, you see it has pleochroism. So it is a biaxial mineral. It is not a uniaxial mineral. That's why it's not a cubic system. It's not a uniaxial system. It's a biaxial mineral. The absorption of the X-ray depends on the orientation of the pyroxenes. So for a single pyroxene, depending on how it is oriented with respect to the X-ray, can show different centered images. For example, here I'm showing you the same pyroxene CPX crystal, one single CPX crystal with two different orientations. And depending on the orientation, you can see the centered energy changes quite a lot. So this induces another uncertainty, a huge uncertainty in the way you can measure ferric iron in the system. So we need to deal with that. This is not a problem for garnet. This is not a problem for glasses, because both of them, glass is amorphous and garnet is a cubic system. But this is a problem for phases like CPX and OPX or olivine and so on, where you have a birefringence, you have a differential X-ray absorption as a function of orientation. So we need to deal with that. The way we dealt with this problem is by orienting all the pyroxene crystals in the same way with respect to the X-ray. And our preferred choice of orientation was having the crystals oriented in a way so that the C-axis of the crystal is normal to the surface of the crystal, and the X-ray comes at an angle of 45 degrees plus or minus 5 to the C-axis. So we oriented all the CPX and OPX crystals the same way so that we can reduce the amount of orientation-induced scatter or orientation-induced uncertainty that can have in the centered image. And when we do that, when we collected the X-ray, the XANES data for all the oriented samples, both for CPX and OPX, we see that the centered energy that I showed you earlier, the create centered energy matches beautifully with or actually increases beautifully with the amount of ferric iron that you have in the system. So this ferric iron have been measured with MOSBAR spectroscopy on our standard pyroxenes, and this is the centered energy of the oriented pyroxene crystals, and it increases linearly both for CPX and OPX. CPX calibration curve at the moment is quite robust because we have about 13 CPX samples that we use, 13 CPX standards that we use to develop this curve. But for OPX, it's still in a preliminary stage, and I can't really guarantee you if this high steep slope is correct, because we're just limited by the number of samples we have. It's very difficult to get OPX crystals which have appreciable amount of ferric iron in nature. So we are still hunting for OPX, more OPX crystals which has 20%, 15-20% ferric iron, just to make this curve more robust. But at the moment, CPX curve is very robust. We have 13 CPX and that we used to develop this curve. So now we tackled one problem, that is, we now know how to measure ferric iron in the pyroxenes in a microbeam method using XANES and using oriented crystals. The second challenge is to grow pyroxene experimentally, right? So the first task, my first task was to measure ferric iron between CPX and melt and OPX and melt in an 1 atmosphere furnace. And what our goal was to grow pyroxenes as a function of to grow experimentally grow pyroxenes experimentally and to do those experiments in different FO2 conditions and to understand if the partition coefficient of ferric iron between CPX and melt and OPX and melt changes as a function of FO2 or it remains constant as a function of FO2. So what we did is that we performed this 1 atmosphere vertical furnace experiments. These are the furnaces where you can these are ambient pressure furnaces. So the pressure is 1 atmosphere, but you can control the temperature, you can control the oxygen fugacity of the system by changing the ratio of the carbon dioxide and carbon monoxide. So you very well know the FO2 of the system, and you also very well know the temperature, and pressure is always 1 atmosphere. So we faced the challenge of growing pyroxenes, because it turns out that the pyroxenes are notoriously difficult to grow. Homogeneous pyroxenes are notoriously difficult to grow from the melt because of the presence of these high valent cations like titanium, aluminum, chromium. They are very slow diffusion species, and they want to make pyroxenes which are highly heterogeneous in terms of their composition. So that's why you see all the sector zonings. But and this is an example. People have struggled previously to grow large CPX or OPX crystals. And you can see here that if we grow pyroxenes at a relatively quick rate, that is, if we cool the system at a relatively quick rate, it grows highly heterogeneous pyroxenes, where the aluminum concentrations and titanium concentrations are changing quite a lot, depending on within the single grain. It's quite heterogeneous. But what we eventually succeeded to do was to do experiments where we cool down the system very slowly, 5 degrees centigrade per hour, and with a long dwell time, we were able to grow relatively homogeneous pyroxenes, which had thick homogeneous rings, where the variation of aluminum and the variation of iron and titanium are very, very low within a system. So they're more or less homogeneous, and you can get thick rings outside of the pyroxenes, or thick pyroxene rings where the variation in FOO or aluminum is very small. So you can put a Zane spot, you can put a electron microprobe spot in there and be sure that that part of the pyroxene is very homogeneous. So we eventually succeeded to grow pyroxenes by doing very slow cooling experiments. And it produced, regularly produced 100 to 150 micron crystals and big melt pools which are free of microcrystals. So you can easily analyze the melt. You can also easily analyze the pyroxenes, for example, the CPX here. So when we did that, after we succeeded in growing these pyroxenes, we measured the ferric iron of the pyroxenes and the melt using using Zanes, and then we determined the ferric iron partition coefficients. And it turns out, very interestingly, is that the partition coefficient of ferric iron between CPX and melt is not constant. So we cannot hold, cannot assume a constant partition coefficient value between CPX and melt as a function of FO2. Remember this, we're talking about partition coefficient, not the concentration of ferric iron. The concentration of ferric iron both in the melt and the pyroxene will increase as a function of FO2 because you have more ferric iron in the system. But not only the concentration, but also the partition coefficient itself increases as a function of FO2. So with increasing FO2, more and more ferric iron prefers to go into the CPX than it prefers to stay in the melt. So as the ferric iron, as the system becomes more oxidizing, pyroxenes become more and more ferric iron enriched compared to the melt. But that is not the case for OPX. For OPX, we see that it's even though individual OPX concentrations, ferric iron concentration are increasing, but the ferric iron partitioning coefficient between OPX and melt remains more or less constant across the FO2. So the take-home message from these experiments would be that we cannot assume a constant ferric iron partition coefficient between CPX and melt, but the OPX melt partition coefficient might be constant across the range of FO2. So this was the first step. But the problem with those experiments were that because we were doing experiments at ambient pressure at 1 atmosphere, they're very low in aluminum. And when we compare the aluminum concentration of the pyroxenes, of the clinopyroxenes, from the aluminum concentration of the pyroxenes that we have in continental xenoliths, we see that they overlap the very low end. So the aluminum concentration of our experimental CPX are very low compared to the xenoliths. And we know previously that aluminum concentration or ferric iron might be coupling substituted with aluminum. So aluminum might have a very important effect in stabilizing ferric iron in the pyroxenes. So we need to grow pyroxenes which has aluminum concentrations that are very similar to what we see in natural periodized xenoliths. So what we did, we set out to do high pressure experiments, but these are more challenging because you have the volumes are smaller and you have less control in the way you can control the temperatures or the FO2 of the system. So what we did for these high pressure experiments, we also wanted to regulate or to modulate the FO2 of the system, and we did that by two different capsule designs. One is very easy, where you can put a silicate mixture, like a silicate glass, in contact with a buffer such as ruthenium oxide. So this buffer has a certain FO2 at a particular temperature and pressure, and which imparts that FO2. Which imparts that FO2 with silicate mixture, and we know the FO2 of the system very well, as long as you have ruthenium oxide at the end. But the problem with this buffer is that it's very oxidizing. It's about delta QFM plus 7, as opposed to delta QFM plus 1, which is about the oxygen acid of the upper mantle. So they are very high in oxygen acid, the ruthenium oxide buffers. We need to do something. We need to make a design where we can reach the FO2 of the system, which is very similar to the upper mantle, so around QFM minus 2 to QFM plus 2 or so on. So for that, what we did is that we used iron platinum alloy capsules. So we used platinum capsules which are pre-saturated with iron metal. So you have a certain concentration of iron metal within the platinum capsule. And during the actual high pressure experiment, the iron in the platinum capsule reacts with the ferrous iron in the melt and modulates the amount of ferric iron in the melt you have. So depending on the amount of iron you put in the platinum capsule would change the amount of ferric iron that you have in the silicate mixture. So this way, by back calculating how much ferric iron you expect in the high pressure experiment, we saturated the platinum capsules with different amounts of iron, and therefore we were able to make silicate mixtures which will have different amounts of ferric iron. So in a way, it's not totally buffered, but in a way, we know that this is the system where you have this particular amount of ferric iron. So therefore, it should have oxidation efficacy of, let's say, delta K +1. So this way, we made capsule design. We designed the capsules in a way that we were able to make able to do experiments where the FO2 of the system is more or less close to the actual oxidation efficacy of the upper mantle. And then we followed a very similar procedure. We followed a very slow cooling technique, just as we developed in the ambient pressure experiments. We cooled it very slowly, and we were able to grow big pyroxene crystals, routinely 100 to 150 micron pyroxene crystals, and big melt pools, which could be easily analyzed by iron zanes. And you can see here, this experiment has both ruthenium and ruthenium oxide left at the end of the experiment. So you know that you very precisely know what the oxidation efficacy of the system is. And for the second design, this is where you don't have a ruthenium oxide buffer, but what you have is an iron platinum alloy capsule. So you can measure the iron content of the capsule and the FeO content of the melt, and you can then calculate what the oxidation efficacy of the system is. So for both of these, we can measure the ferric iron of the glass for the pyroxenes, and we know what the oxidation efficacy of the system is. And then we can determine the partition coefficient is. And more importantly, what these experiments did is that because they were done at high pressure, between 1 to 2.5 GPa experiments, they made pyroxenes which are more luminous than our previous experiments. So the range of aluminum concentration of these pyroxenes matches or overlaps with the aluminum concentrations that we have in the periodic xenoliths. So they're more closer to the actual reality. And also, just as a side note, you can the way we confirmed that the system reached FO2 equilibrium is by measuring FO2 in two different ways. One by measuring the iron platinum alloy, and the other by actually measuring the ferric iron in the glasses. Which we can then translate to the amount of ferric to the oxidation efficacy of the system. And these two independent ways of calculating oxidation efficacy correlate very well with each other. So we know our system or our experiments reached FO2 equilibrium. Both the capsule, the silicate melt, and the CPX crystals or the OPX crystals, they all reached FO2 equilibrium with each other. So that's a sanity check for our experiments. So now that we measured all of these, measured the phases, we can then calculate the partition coefficients and between CPX and melt. And it turns out very similar to what we found in ambient pressure experiments. The partition coefficients are not constant. They are a function of the oxidation efficacy of the system. They are a function of pressure. For example, if you look at the overall trend, it looks like with increasing oxidation efficacy, ferric iron becomes more and more compatible in CPX. So the ferric iron partition coefficient goes up. But even if you look at, so that's one effect. The other one is that if you look at the particular FO2, let's say from 0, you can see that the ferric iron partition is increasing, partition coefficient is increasing as the pressure is increasing. So there's a pressure effect, there's a delta, and there's an FO2 effect as well. So both of these effects together causing the ferric iron to become more compatible in CPX, pressure and FO2. Both of them have a positive effect on increasing ferric iron partition coefficient. So what we tried to do is to then compare that with previous experiments. So there has been no high pressure experiments where people have previously measured ferric iron accurately with zanes or other methods. So we do have a very limited background knowledge about this problem. But there is a very recent study by Davis and Cottrell 2021 where they have indirectly determined the ferric iron content of the CPX and OPX, and therefore have measured the partition coefficients. And we see that our partition coefficients are much smaller than what they found, even though the pressures were very similar to ours. But I must tell you one fact that, which I'll show later, that the pyroxenes will have the pyroxenes of Davis and Cottrell have very different aluminum concentrations than our pyroxenes. They're very rich in aluminum than our pyroxenes, which turns out have a positive effect on the amount of on the ferricurrent partition coefficients. So when we compile all the data of our experiments and theirs, we see that irrespective of the pressure and the effect of the system, there is a positive correlation between the amount of aluminum concentration that we have in the CPX and the CPX melt ferricurrent partition coefficient. And then when we plotted the Davis-Petrel data, it makes sense, right? Because Davis-Petrel has much higher, their pyroxenes have much higher aluminum concentration than our pyroxenes, and it is expected that those pyroxenes will have, or those experiments will have higher partition coefficients because they are high in aluminum concentrations. So there is a huge effect of aluminum in CPX that is controlling the CPX melt ferricurrent partition coefficient. And I won't go into too much detail into this, but this is just as a side note. When we compare the ferricurrent partition coefficients with the existing thermodynamic models, such as PMELS and PARPLEX, just because as I told you, we don't have a lot of experimental data to compare with. So what we compared with is previous theoretical thermodynamic models, such as PARPLEX and PMELS. We see that both PMELS and PARPLEX hugely overestimate the CPX melt ferricurrent partition coefficients. They're always, irrespective of the FO2 or the pressure, they're always higher. They always give you higher values of ferricurrent partition coefficients than what we found experimentally. So something is wrong with these experiments. Something is wrong with those thermodynamic models. If you use those thermodynamic models to get the ferricurrent in the pyroxenes, you'll always get overestimated values than what we found in our experiments. And the reason is, when we try to understand why there is a correlation between aluminum concentration and ferricurrent partition coefficients. And we did that by calculating the two-element partition coefficient, which is KD. So the KD is the ratio of ferricurrent and aluminum, the ratio of ferricurrent and aluminum between CPX and melt. So ultimately, the KD becomes the ratio of ferricurrent partition coefficient and the ratio with aluminum partition coefficient. But we see both in thermodynamic models as well as in our experiments, what we see is that as the system becomes more oxidizing, the KD value goes up. What does it mean? It means that the ferricurrent becomes more compatible in CPX compared to aluminum. So the ratio goes, so this ratio actually goes up with increasing FO2. So the ferricurrent becomes more compatible than aluminum compatibility, which is true for both our experiments as well as both thermodynamic models. But notice that they're plotted in different scales, right? The experiments, the thermodynamic models are plotted on the left axis, the experiments are plotted on the right axis. And notice the numbers are very different. So the thermodynamic models predict that the ferricurrent is always much more compatible than aluminum in CPX. So irrespective of the FO2, it is always greater than 1. The ratio is always greater than 1. But what we found is that that's not true. What we found is that at low oxygen fugacity, aluminum is more compatible in CPX, so the ratio is less than 1. But as we go up above delta KFM plus, above delta KFM 0, the ratio starts to becoming greater than 1. So at higher oxygen fugacities, the ferricurrent becomes more compatible in CPX than aluminum. So aluminum does have a very important role to play in stabilizing the ferricurrent. The aluminum, the ferricurrent replaces the aluminum in the tetrahedral site as the system becomes more and more oxidized. And that explains the positive correlation between aluminum concentration in the CPX and the CPX ferricurrent partition coefficient. So nonetheless, what we did is that we then fitted the correlation that we found between ferricurrent partition coefficient and CPX aluminum with a simple linear regression, and then we used it to model what the ferricurrent partition coefficient, and then we used it to model the ferricurrent content of the basalts that would be generated by partial melting of peridotite. And I will go too detail into that, but just as a note that in order to get the ferricurrent partition, in order to model the ferricurrent partitioning during partial melting of pleurodite, we need to know a bunch of things. For example, we need to know the individual mineral melt partition coefficients, like the Ds, and we need to know the weight fraction of these individual minerals. For CPX, we know the Ds directly from our experiments, and for spinel, we know the D from a previous experiment of reducing Petrel. But for garnet and OPX, we don't have any direct experimental data to measure this value. So we relied on the CPX data to tell us what the garnet melt or the OPX melt partition coefficient will look like. For example, I'll just give you one example. The OPX liquid partition coefficient is a multiplication of OPX CPX partition coefficient and CPX liquid partition coefficient. CPX liquid partition coefficient we know from our experiments, and OPX CPX partition coefficients we calculated from the xenolith data. So using these two, we then tried to model what the OPX liquid, or we calculated what the OPX liquid partition coefficient would be. Similarly for garnet. And then we tried to model what the basaltic, what the partial melt ferric iron content would look like if we melt a pleurodite with a certain ferric iron. And we see that, and when we compare that, so we did those calculations for 3 different potential temperatures from 1320 to 1440 with very different source ferric iron value. So the source ferric iron varies from 0.02 to 0.06 for 3 different potential temperatures. First thing to notice is that these are the red diamonds are the natural MORB data, and we were trying to compare our model curves with the natural MORB data. The first thing to notice is that our model curves generate this negative trend. It is a similar trend that we observed in the natural MORB data, and that negative trend is caused by the fact that as we melt this pleurodite more and more, so this is a low degree melt and this is a high degree melt. As we melt the pleurodite more and more, the CPX percentage goes down, the CPX aluminum goes down, the spinel concentration goes down. So all of these effects is causing the ferric iron to become more and more incompatible as the degree of melting progresses. So here at the very low end of the melting, at a very low melt fraction, ferric iron is highly compatible because you have high CPX aluminum, high spinel concentration. But when you reach about 15-20% melting, you have low CPX left. CPX has already depleted in aluminum, and you probably have no spinel. That's why the ferric iron has become more incompatible. So you have so that's why it generates this negative trend between ferric iron and sodium. And another thing, the question that we had started with was, what is the ferric iron content of the upper mantle? And that we answer by calculating all these model curves for very different source ferric iron concentrations. And we see that a source ferric iron concentration of 0.038 plus or minus 0.007 explains or covers the largest amount of MORB data, natural MORB data. So essentially what it means is that for 3 different potential temperatures and a source ferric iron concentration of 0.38, that covers the maximum amount of natural MORB data that we have. So that is, at the moment, that is the most likely value of ferric iron content of the upper mantle that is generating the Belson results. And when we now go back to our original question of what the ferric iron content of the upper mantle looks like, and we compare that with previous estimates, we see that our value is not very different from what people have estimated for the continental lithospheric mantle. Remember, the continental lithospheric mantle has about 0.02 to 0.034, and our preferred value is about 0.038. So we postulate that the ferric iron content of the asthenospheric mantle is not very different from the ferric iron content of the continental lithospheric mantle. They're very similar, which is about 0.038. And lastly, I want to address this last question that we have, that is why OIBs are more oxidized than midration-rich basalts. And we explain that by the fact that we extend these calculations to high pressures. So right until now, we have been doing these model calculations until about 2.5 GPa. And now we extend those calculations to 4 GPa, which is roughly the region where ocean island basalts are generated. And you see that when we plot the ferric iron content and the sodium concentration of these model curves, so these are the modeled calculated ferric iron content of the model melts, we see that at at very high pressure, where like more than 2.5 to 3 GPa, where garnet is stable, the system becomes the ferricurrent becomes very incompatible. The reason why? Because the garnet takes up most of the aluminum from the pyroxenes. So it takes up most of the aluminum from the pyroxenes. The pyroxenes, the CPX, both the CPX and the OPX become aluminum poor, and therefore their capacity of holding ferricurrent diminishes. So if you melt the pyrrhotite in the presence of garnet, you actually lose more ferricurrent. The system becomes more incompatible in ferricurrent. So the melts become highly enriched in ferricurrent. So it doesn't mean that the system has more ferricurrent or the system is more oxidized inherently. It just means that the system has garnet present, which causes the ferricurrent to become more incompatible, and therefore when you melt it, the melt has more ferricurrent. And when we compare the model curves with our natural ocean island basalt data, for example, Iceland and Hawaii, we see that the Hawaii data or the Iceland data can be generated by extrapolating these curves to high melt fractions. So these are, or at least part of these oxidized nature of these OIBs from Hawaii or Iceland could be from the fact that these are generated in presence of garnet. Therefore, ferricurrent was more incompatible in those systems. However, there are other systems such as Canary and parts of Iceland, which are too oxidized to be generated from our model. So they are still quite highly oxidized compared to when we compare with our model curves. So they surely cannot be generated by just by melting of a normal pyrrhotite. There is probably some other lithologies that are present which are inherently more oxidized compared to an ambient pyrrhotite. But the conclusion is that before we can talk about the source heterogeneity, we need to talk about the fact that the melting itself can generate difference in ferricurrent concentration in the melt as a function of conditions in which the melting is taking place. So that's answering all the questions we started with. So I'll just briefly summarize my talk. So we saw that the pyroxenes are the chief reservoir of ferricurrents. So in order to understand ferricurrent partitioning, we need to understand ferricurrent partitioning between pyroxene and melt. And Zanes is a potential method of precisely measuring ferricurrent at microbeam scale. But for that, we need oriented pyroxene crystals, both experimentally as well as like oriented standards, as well as experimental oriented pyroxenes. And at high pressure, when we do high pressure experiments, we see that the pyroxene melt partition coefficients are not constant. They vary as a function of FO2 pressure and CPX aluminum concentration. And when we try to model that, model the MORB ferricurrent content, we see that the negative correlation between sodium and ferricurrent in the MORB is a natural consequence. It's a natural consequence of varying ferricurrent partition coefficient as a function of degree of melting. And the last thing is that the ocean island basalts are oxidized compared to the mid-ocean basalts, and some of the oxidized character of the ocean island basalts could be because of the fact that ocean island basalts are generated in presence of garnet, and not because of the fact that they are coming from an inherently oxidized source. So with that, I'll thank you everyone for your attention, and I'll happy to take questions.
Okay, thank you, Avishek, for your talk, and that's time questions for our participants. So feel free to open your mic or type a question in the chat. So also, before you ask a question, feel free to briefly introduce yourself about your name and your institution. So go ahead. Any questions? Okay, before everybody asks, other participants ask question, I would like to go with two questions from my side. So one question is related to one slide that you show the difference in terms of your modeling by P melts and purple X and the measurement, experimental measurement of the ferrous iron in the CPX as well as in the melt they have shown. And for that contrasting difference, I know that it caused due to the lack of the ferrous iron data in the P melts thermodynamic database as far as I could think about. But I know that in the very limited data that they had for both P melts and purple X, so how did they calculate this for ferric iron? So what type of data did they use that lead to this results?
Yeah.
Because this
So,
one that it shows really incompatible ferrous iron using their
so,
data.
so
So
females,
what type of data that lead to this result?
yeah, that's a great question actually. So females uses very old, I think 1986 experiments at 1 atmosphere. So those are experiments that were done between very alkali pyroxenes, like very alkali systems, which are very rich in sodium and potassium. Those pyroxenes are very rich in sodium and potassium. So it is based on experiments, but those are very old experiments, which were, I'm not saying they're bad because they're old, but they're bad because they are pyroxenes which are highly zoned, highly sector zoned, and which are highly rich in alkalis. And not only that, the most important part is that the ferric iron content of those pyroxenes have been measured with electron microprobe. So there could be multiple different, and they, of course, result in, those experiments produced, they infer, the experiments told us that the pyroxenes are always, the ferric iron is always compatible in pyroxenes. They're always greater than 1. The partition coefficients from those experiments are always greater than 1. And I do not believe those experiments to be true because of multiple reasons. Because of the fact that the pyroxenes, the ferric iron of the pyroxenes was measured with electron microprobe, and at that time there was the old generation microprobe, which has a very poor accuracy. And the other thing is that the pyroxenes were strongly zoned, strongly sector zoned. So depending on where you put your microbeam, you can get very different answers. So those are from females. Those are based on experiments, but the experiments were not great at that time. I mean, it's limitations of their time, not limitations on the part of the researchers. And the Perplex data actually come from natural samples. The Perplex data come from natural xenoliths, which is probably why it predicts the ferric iron partition coefficients better than females. So Perplex data come from MOSBER data of natural mantle xenoliths, but it doesn't come from experiments. But females purely comes from one single study by Richard Sack and here, so 1986, and those experiments were bad.
Okay. Actually, another question that I'd like to ask. I remember a couple of years ago that I heard Paul Asimov at Caltech talk at several occasions talking about the ferric iron crisis, because in my interpretation, his argument that according to the mantle partial melting model of the ferric iron, then the oceanic crust thickness won't be the same as the oceanic crust that the geophysicists observed. So did your work that help him to reconcile the geophysical observation and the ferric iron partitioning?
Actually, that problem, that's again, it's a good question, because that problem, so Paul Asimov has written a book chapter in 2021 exactly addressing this problem. It's one of the Wiley book chapters. But that problem doesn't come from ferric iron in the pyroxenes or spinel. It comes from the fact that there is ferric iron in basalt. So all the previous models of Asimov and Herzberg and Asimov et al., they assume 5% ferric iron or no ferric iron at all in the basalts. But the moment you have 14% ferric iron, all the KDFENG between olivine melt, all the thermometers that have been developed, that breaks down, because now you have 14% ferric iron, which you need to take into account. And in that chapter, he describes it's an unresolvable problem, unresolved problem. It's not unresolvable, but it's an unresolved problem till now. Because in that chapter, he quantitatively describes what the problem with the existing model is. So at this moment, if the basalt has 14%, if the mid-oceanic basalt has 14% ferric iron, and if the oceanic crustal thickness is, let's say, 7 kilometers, and if the potential temperature is 150 degrees, let's say, they are irreconcilable. You cannot reconcile all of these factors together. So something is wrong with either one of them. Either the ferric iron is less in basalts, either the mantle potential temperature is different, or either the crustal thickness, which is unlikely to be false. But either the current models of understanding basalt generation is not totally correct, or either we are overestimating the basalt ferric iron. So it's currently an unresolved problem. But if you go to the book chapter, he describes it more quantitatively to what extent the problem is. Yes.
Okay. Other questions from other participants today? Feel free to open your mic or leave your question in the chat.
Hello, I have a question. Yeah. Based on your results, you said practically the origin or the source to generate the OIB and the MOIB are practically equally oxidized or let's say equally reduced. But is it contradicted to the composition character which reflected the mid-ultralight salt and also the OIB salt? Because the mid-ultralight salt in general is, for example, for rare earths is heated compared to OIB composition, which reflected the nature of the source. That is, the OIB source mantle should be more, let's say, depleted, which can be referred to or reduced, then vice versa. How do you explain that?
Yeah, so when we try to tackle this problem of why YBs are more oxidized than mid-ultralight salts, we knew that there would be a component of the source that is causing the YBs to be oxidized. But what we wanted to address is there is surely, or there is very likely to be an effect of melting as well. So we only address that part of the problem or that part of the question of how melting can influence the different how melting can influence the ferric iron content of the melt. So our model explains the fact that some of the difference between OIB and MORB can be caused by the fact that YBs are generated in presence of garnet. Some of the YBs are generated in presence of garnet at a deeper pressure and represent a smaller degree of melting. But still, we are not ruling out the fact that because there is a source heterogeneity in the YBs, that is also causing the YBs to be more oxidized. We're just saying that that difference between YB ferric iron content, some part of the difference could be or is actually coming from the difference in melting conditions. However, rest of the part should be coming from the fact that the YBs have a different source. Some of the YBs have a different source material in their mantle. So yeah, we're not ruling out that at all. We're saying that there is another component, which is the fact that the melting conditions are different.
Yeah, because I mean, there's clearly a difference, for example, in isotope composition.
Yes, yes, but then you have to understand, you have to separate out between the amount of ferric iron you have and the oxygen acid of the system. Both of them are not always one-to-one correlated, right? For example, if you have a mafic lithology in the source of the ocean island basalt, it might have a very different ferric iron compared to the rest of the ambient peridotite, but the oxygen acids of the mafic lithology, let's say eclogite, could be very similar to the peridotite, just because the way the mineralogies are. The eclogite has mostly omphocytic pyroxenes and garnet, whereas peridotite have garnet, CPX, OPX. So even though the bulk ferric iron content of the mafic lithology is very different from the bulk ferric iron content of the ambient peridotite, the oxygen acids could be similar. So it's not always a one-to-one correlation that that a lithology which is having a higher ferric iron would also have higher oxygen acid.
Yeah, thank you. Yeah, it's very interesting observation, but I think if you draw a conclusion in general, have to be more conscious. Yeah, thank you very much.
Okay, I think that's Su Chao, physical in Germany. Okay, next question is from Zerun from Institute of Deep Sea Science and Engineering, Chinese Academy of Sciences, and he lost on the second last slide and how to understand the ferric iron to iron ratio increases with the sodium oxide in the garnet stability field. Basically, that's asking you to explain a bit more about your explanation, basically for the YB water source.
So they're talking about this part, these curves, right? These are the curves where, yeah, if I understand the question correctly, why ferric iron is, why the melts are more enriched in ferric iron in presence of garnet, and that's because of the fact that whenever garnet, so okay, so first thing first, these are currently, from at least from the perspective of garnet, these are empirical models. We know the ferric iron partitioning between CPX and melt better from experimentally. We know the ferric iron partitioning between spinel and melt better. They're also from experiments. But for garnets, they have been calculated indirectly, just the way I showed earlier. So these are still empirical models. But the reason why our model curves have higher ferric iron in presence of garnet, because once you stabilize garnet in peridotite, the garnet takes up most of the aluminum from the CPX and aluminum, CPX and OPX. So as the CPX and OPX becomes aluminum poor, the ferric iron, because aluminum in CPX is directly related to the ferric iron partition coefficient, the ferric iron compatibility goes down. So in presence of garnet, because garnet is taking out most of the aluminum, the bulk ferric iron partition coefficient between peridotite and melt is going down. Ferric iron is becoming more and more incompatible. So for a similar degree of melting, for the same degree of melting, let's say we melt 5%, we melt a source 5% in presence of garnet versus in presence of spinel, you'll always have the melt having higher ferric iron if garnet is stable, because garnet is taking up most of the aluminum and the pyroxene aluminum poor. But having said that, we still don't understand the garnet melt ferric iron partition coefficients better. We need to understand that better before we can quantify this effect. But right now, as it stands, we saw that because garnet is taking up most of the aluminum, it's causing ferric iron to become more and more incompatible, and therefore the melt is becoming more enriched with ferric iron. If that answers the questions.
Okay, any other questions? If not, I think we have already run 60 minutes for this webinar. That's pretty good. So thanks again for speaking today, and thanks everyone for the participation. So could everyone open your video, to smile to our speakers to show our appreciation for 30 seconds, and then we could end the meeting.
I need to stop sharing the screen. How is
Yeah, sure. Yeah, we were just going to keep this meeting for another 30 seconds so that you could see your audience faces. Yeah, you could stop sharing. I think then it's easier for you to see.
Wait, how do I know how to share, stop the share, but I'm not able to do it. There you go. Wait, there you go. It was hidden.
Yeah. Yeah.
Awesome.
Okay. Thank you again. Yeah. Have a good day, everyone. And yeah, and I hope to see you in the coming webinars. Thanks for your participation.
Thank you, everyone. Thank you, Johnny. Bye-bye.